Welcome back to the third video. I'm also recording this because I really love the problem at the end. I'm weird, but I think it's kind of fun. All right. So what we're going to have here is a kind of special, interesting side effect result of long division or synthetic division. So check it out in here. So the first one is they said, all right, if we focus just on dividing by x minus c, which would be a nice factorable linear factor, if it is a factor, then the result I get by plugging in c should be 0. But check it out. Even if it's not a factor, look at what happens when we plug c into this for x. So I've got f of c equals now it's c minus c, which is going to be 0, times q of c, which I don't even care what it is, plus r. So we get f of c is the remainder that I get when I finish with my crazy division. So I take my original function, whatever it is, and I'm going to divide by x minus c, or since we're specifically focusing on linear factors, we can use synthetic division here. And what I get is the remainder is, formally we would call that the function value. Because remember, you guys have been graphing functions, function notation, f of x. X is the first number in the point. The result is the y number in the point. So what this is also telling us is that the point c comma r, c being the set it equal to 0, move it over number, r being whatever the remainder number is, because we're dividing by a linear, the very last thing would be just a number. It couldn't be more than a number. Like it couldn't be x and a number like the way we saw with the squared one, because what we divide by, the divisor would have to be a larger power to get more than just a number for the remainder. So this gives us an ordered pair point on the graph. And by knowing that, that's another way to realize what these zeros are, what they mean graphically. This is also way back in the day how people would figure out function values. For polynomials, like really big polynomials, is you do synthetic division with the value you wanted. And it just works out really nicely. And it actually doesn't matter what kind of craziness the value is in. If it's a square root, you can still do this. Even if it's, we're going to see down below, a complex number, you can still use synthetic division and do it. Crazy. But here we're going to check 5 and -3. So those are the c values themselves. I don't need to switch the signs on those. So this is asking me here for when x is 5, f is what? That's what f of 5 means. Or you could think of this as the y value associated with 5. And we're just going to use synthetic division for that. 5 in the box. And then we have our nice, let's just double check, 4, 3, 2, 1, 0. Everybody's accounted for. I just got to copy my coefficients. A 1, another 1, -6, -5, -15. And we're going to do the same thing over here with the f of -3. But we'll continue on with our first one first. Bring it down, 1, multiply. 5, 6, 30, woo! So this is 24 now, oh my good Lord. 5 20s is 100, 5 4s is 20, so this is 120. And that's 115. This is where I would get the calculator. But that is 550 and 75, so 575. Whew. So 575 minus 15 is 560. 560 is the remainder here. And remember, our remainder is f of c. C was 5, so f of 5 is a whopping 560. Now, if you graphed that on the calculator, you went over to the table function, you typed 5 in, it's going to tell you 560 back out. Appreciate how quickly and nicely that gives you the results you want. You want a different F value, you type in a different F value. There is a setting in the table function on TIs. I know there's one on Casio, I just don't know where it is on a Casio. But on a TI, under table settings, which is another one of the shift on the F keys, the top row, it has an option that says independent or auto. Automatic means it automatically generates the X values and it just puts integers in there and starts at 0, which if you just want to know an integer, you can just scroll up and down and find it in your list. I personally find that annoying though, because if I want to know what 100 is, I do not want to scroll to 100. If you change it to ask, you just type in whatever values you want, which include square roots, which include decimals, fractions, whatever you want. If you type a fraction, it will automatically convert it to a decimal and put the decimal in the table. It doesn't have a way to render fractions or the square roots. It'll put the decimal. I'm sure eventually a fancy calculator will be able to program in complex numbers, but I have yet to see one really. There's that. But you would very quickly see 560 is the function value. That means 5, 560 is the ordered pair here. So I'm going to type that in because 560 is huge and because I can't. So we'd go over 5 on the X and then way up to 560. That's a very high number. All right, now same song, second verse with -3. So put the -3 here. Copy the coefficients again. 1, 1, -6, -5, -15. Bring it down and multiply, add, multiply, add. -3 times 1, -3, add -2, multiply 6, add 0. Oh, multiply 0, add -5. -3 times -5 is a +15, and there we go. There's that 0. So -3, 0, and I'll write that in, is a point on the graph. Now think about where is that point? If I graph -3, 0, that is a point on the x-axis, which makes that an x-intercept of the graph. That is why we call it a 0, because the y value, the function value, is 0 at that point. And it means that number flipped back over, x plus 3, would divide nicely, is a factor of this huge polynomial. And in fact, the result would then be, it was x to the 4th, so this is x cubed minus 2x squared plus 0x minus 5. That times x plus 3 gets me back to the original function. So this can be useful, especially back in the day before graphing calculators. This was really useful for generating points on polynomials. And you could even use it on the rational functions. You just do it as 2 separate steps and then just divide whatever the results were. But that's what people had to do to land astronauts on the moon. If nothing else, I want you guys to have an appreciation for the sheer amount of work those lovely women did. All right. So here, just to be perverse and a math teacher, we're going to do this with a complex number because we can. Is this really useful? Not that I've seen, I just find it fun. So if you don't want to watch, it's okay. I'm putting it on here in case it shows up on your homework. I don't know if it will. If I was designing your homework for college algebra, I wouldn't put a complex number one just because it's like, why? Just because you can do something doesn't mean you should. All right, so they tell us C equals 3 plus I. So that is what I'm going to write in the box, as it were. And then our coefficients, cube, squared, linear, constant. All right, we got all of those. So a 1, a -7, a +16, and a -10. So the process is identical. It's just what we're going to be writing underneath those is going to look a little bigger. And we're probably going to have to take some stuff to the side and work the multiplication out. First step is still the same though. Bring down the first one, multiply. The thing times 1 is the thing. So we're going to write 3 plus I here. And then we're going to add those. So the -7 and the 3 combine, the I is just going to hang out. So that becomes a -4 plus I. And here, because we're going to have a lot of stuff there, it is totally fine if you want to write each of our terms going along in parentheses just to make sure they don't get smushed. So now we have to do 3 plus I times -4 plus I. Box. Nobody wants you to do that mess by hand. Like in the moment as you're doing it, because we're going to combine like terms. We're going to have an I squared that flips the sign, and we're going to get a complex number out of this, but certainly do this to the side as scratch work. Don't try to squeeze that in somewhere in there. There's not really a spot for it. And then plus 3I, and then plus I squared. But I squared is -1, so this becomes -1. And I just change it right then. If it was 4I squared, then I would be, if it was plus 4I squared, then beneath it, I'd write -4 and I'd cross out the I squared term. So -12 minus 1 is -13. And then 3I minus 4I is minus I. So a -13 minus I. And again, if you want the parentheses up here, by all means, you could even like draw in some lines just to be extra careful about where stuff happens. Alrighty. So now I'm going to add 16 plus -13 is a 3 minus I. Aha, that is very, very close to our C. 3 plus I, 3 minus I. Let's see. In fact, some of you guys maybe, it's a difference of squares. You don't need to write the box. I know. I like writing the box. So 9, 3 i's, -3 i's, minus I squared. Negative times I squared is -1 will be +1. So +1. 9 plus 1 is 10. 3i minus 3i is 0. So we get 10. So we get 0. So I got a 0 here. That tells me 3 plus I is a 0. Which means x minus c, which in this case would look like this, is a factor. Now, we normally don't write factors with complex numbers. So if I made the other guy I saw over here, its conjugate, that's why this worked out to just a number. In order to get back to the original function, if 3 plus I is a 0, or sometimes we call it a root, then 3 minus I is also a root in order to get back to this lovely polynomial with no i's in the original. That's the only way to balance that out, is to have its conjugate. And if you think back to the quadratic formula, like those are the way the answers always look. It's plus or minus. If there's a coefficient in front of the I, fine, but it's always plus or minus that I. And the number in front stays the same. So those roots always occur in pairs. All right. Now, as you guys are looking at more crazy polynomials, you're going to see like double roots and triple roots, or what we call multiplicity, and it's going to do crazy things to the graph where it's going to cross or it's going to bounce. And you can actually like roughly sketch the graph and figure out how it's going to look. That does have a little bit of use in pre-cal, and I found it really useful because you can garner the same information from calculus just a different way by using the derivative. And is the slope positive or negative, then it's going up or down. Is the concavity positive or negative, then it's curved one way or the other. So all of it together, you can actually get a beautiful looking picture of the function. You can tell where the zeros are, where the tops are, where the bottoms are, the highs and the lows. Like it just all works out nicely. So the last problem type, my favorite here, is what's called designer polynomials. That's what I named it. And I named it because I'm asking you to design a polynomial with these specified conditions. So this in particular may not use it that often, but the idea behind it, having to design something that meets specifications, is certainly something you do in a job, at least any job above a certain level. But honestly, even entry-level jobs, you still have to solve problems. You have to meet customer demands or specifications. So we all do it. So I want to write a polynomial. I say of degree 3, meaning there are at most three factors, but since we're including complex numbers, there are exactly 3 factors. But I want my result to have integer coefficients, and I want it to have these zeros. So one of them is a fraction, y, because I'm weird, and the other is a complex number. But there's only 2. Yes, I did that on purpose, because of all the blah, blah, blah I was just saying before about conjugates come in pairs. So if 1 plus 2i is a root, or is a 0, 1 minus 2i must also be a 0 to get us back to the integer coefficients, real coefficients. So we are going to start with those 2. Each of these is zeros. That means the function has a 0 when x equals these things. So I start with, so x could equal 1 plus 2i. X could equal 1 minus 2i. And x could equal 2/5. So if I think about this problem in reverse, if I had the original function and I knew I had a real root, you could actually use the calculator to figure out where that is. Factor that out, the result would be a quadratic. You use the quadratic formula, you get these 2 complex roots. So you would end up with like x equals 2/5, but the step you would have before that could be written as a factor equal to 0. So all of these, I want to get them back to the equal to 0 point. So over here, I'm going to minus the 1 and minus the 2i. So I end up with x minus 1 minus 2i is equal to 0. I'm going to sketch in the parentheses there. So that is a linear factor, one way to write a linear factor of our desired designer polynomial. Now I could also like multiply that whole thing by 3 or -4. So there's always this idea of you can put some constant multiple in there, but overall, there it is. There is a factor. Same song, second verse here, minus 1 and plus 2i would be equal to 0. So there's our second factor. We are going to box those together. This in particular is why I love the box method. And then this last guy over here, a little more interesting. So I could just move the 2/5, and that would be one way to write a linear factor. But the problem is then I have a fraction. And in the problem stem, I said integer coefficients. So if I multiply through with that fraction, I'm not going to have an integer coming out. So what we're going to do first is actually think about how would I get 2/5 normally? Like, how do I get the divide by 5? Why do I divide by 5? I usually divide by 5 because I had 5x on the line before. So that is our first step. We're going to multiply both sides by 5. So now I have 5x equals 2, and now I will minus the 2 over. So 5x minus 2 is equal to 0. So that would be our third factor. So once we get the result from this ugly mess over here, we're going to multiply that to 5x minus 2. Now, because we have the conjugates over here, this should work out to all real coefficients, and then multiplying by something with real coefficients will be good. So I don't know what the polynomial is, but I know where it's going to come from. It's going to come from multiplying this, this, and this. Okay, so let's start it out. X minus 1 minus 2i, x minus 1 plus 2i. And I will say, I may not have used this in particular, but I have in the past actually for a friend. We were working on a project and I did have to design some functions to meet some specifications because he was trying to write a program onto a Raspberry Pi board, and Raspberry Pi board only has so much room, and the more steps you have to do, the more room it takes up. So he was wanting me to be able to reduce it to a more simple function, which I managed to do, mostly. All right, so x times x squared, minus 1x, minus 2ix, minus 1x, plus 1 now, ooh, plus 2i, then 2i times x, 2ix, but it's positive, and then minus 2i, and I want you to look, there are a bunch of terms that cancel out. Everything that had an I there is going to go away. Then the last one here is minus 4, and I squared. So my in-between kind of thought here is negative 4 times negative 1, so this is 4. I'll even put the plus. All right, so I have an x squared. I'm going to write this off to this side here. I have minus 1x, the 2ix, and the minus 2ix, but those guys cancel. So just minus 1x is minus 2x's. All right, used those. Then I have the minus 2i, the plus 2i, those cancel. So I have 1 plus 4 is 5. So those two ugly complex things, when I multiply them together, I get x squared minus 2x plus 5. So if I did the quadratic formula with that, I would get 1 plus 2i and 1 minus 2i as the answers, the solutions from the quadratic formula. It's like all the stuff we have been learning is like the forwards and backwards or sideways ways to get towards the same ideas. So finding the roots or the solutions of an equation is very often the answer to a problem. When you design a function for something, eventually you end up having to solve it. Even if you're not setting it equal to 0, you move the thing you're setting it equal to over, and now it's equal to 0, and everything we've been learning about how to solve these comes into play. Or you just type it into Google, Google asks Wolfram Alpha, and that spits out the result with a pretty graph, 20 decimal places. Yeah, don't know why we do this by hand. No one does anymore. All right, so this is still not the polynomial, but it is integer coefficients. So now I'm going to take that x squared minus 2x plus 5 and that 5x minus 2. I'm going to box those together and get my answer, or one of technically an infinite number of answers, but they're answers in a specific way. All right, so x squared minus 2x plus 5, 5x minus 2. I find there's something satisfying about doing a multiplication and like knowing it, you know, it meets the demands required of me. I did the thing, I did it well, I did it nicely, it came out. It's just satisfaction in knowing you did it. So I hope you guys get that feeling. 5x x squared, that's 5x cubed. 5x minus 2x will be a minus 10x squared. Double check the powers on the x's, because sometimes you guys tend to misplace one of the powers. But within a row or within a column, you should not see any like terms. So if this is an x cubed, I should not see another x cubed. Now down here, minus 2x squared, so minus 2x squared. Now it's okay that these guys catty corner diagonal are like terms, just no column or no row should, if you've done your multiplication correctly. Plus 4x and a minus 10. And we're just going to collect the like terms and have our answer. 5x cubed minus 10x squared minus 2x squared is minus 12x squared. 25x plus 4x is a whopping 29x. And then we just have our minus 10. So there it is. 5, negative 12, 29, and negative 10 are all integers. And if I graphed that, I could see it going through between 0 and 1 at 2/5, 0.4. And then the complex roots, you will not see it cross the axis, but you'll see it make a nice little dip either above or below the axis. I think in this case, it would be probably, I don't know. One starts positive, goes through. On one or the other side, but the overall shape of the graph is going to be like that. I just don't know whether the intercept would be up here or down here for where it crosses the graph, because you can just pick it up and move it, but that'll be the shape. All right. So that's the crash course in the weird designer polynomials. Again, this may not be on your homework. I really just covered it because I like it. So if you watched through the video, hopefully you are enjoying math as well in some weird way. If not, I did tell you guys you didn't have to watch this video at the end of the last one. All right. I'm proud of you guys. Stay strong, stay safe. I know you guys did great on your test, or you will do great on your test depending on which class you're in. All right. Peace.